So now we move into chapter 13. It's a very practical way of handling radiation, heat transfer problems. It's basically radiation exchange between surfaces. Down here, we're going to have participating medium, but I'm just going to tell you right up, we're just going to skip it. The challenge is to analyze the radiative heat transfer between surfaces in an enclosure. You could have 2 surface enclosure, 3 surface enclosure, multiple surfaces enclosure. But when you get above 3, it gets a little, very difficult actually, bookkeeping wise. And I've never had an exam that I can remember where I had 4 or more surfaces that made up the enclosure. It's typically just 2 or 3. Okay? Maybe you can get a 4 surface enclosure. But definitely 5 and beyond, forget it. It's just not going to be on an exam. Oh, for a computer code? No problem. Let's implement it. Let it chew on it. You know, it'll do the work for us. The first part is the most important part. It's the view factor. So the view factor is given a symbol F, and you have 2 subscripts, I, J. Sometimes I'll put a dash between them, but the book doesn't. It's just IJ. It's not like the IJ component. It's the view factor can have 2 distinct meanings. One is very physical, one is very mathematical. We're going to get to both of them, and we're going to use them back and forth. Okay, we're going to be like bilingual. You know, sometimes we'll speak this language, sometimes that language. Sometimes we'll talk about the physical attribute of the view factor, sometimes the mathematical attribute. Okay, what's the physical? The physical is something like this. Q, that's as many photons, or the power, something like that. Energy, radiative energy, leaving surface I that goes and hits surface J, impinges on surface J. And if you divide that by all of the photons that leave surface I, all of them, and go to any surface J in the enclosure, then I get a ratio, I get a fraction. It's dimensionless, and that's the view factor. What's the view factor? The fraction of radiant power, or the fraction of photons, or the fraction of radiant energy, or energy per unit time, that goes from surface I to a particular surface J. So it's normalized for all of it leaving I. All right. The other is mathematical. Let's say, oh, the view factor I to J is equal to 1 over the area I, double area integral of the cosine theta I cosine theta J divided by pi r squared dAI dAJ. So you're going to integrate over the area I, you're going to integrate over the area J. It's a double area integral. I challenge you. You go to your calculus textbook. You said, I learned calculus like the back of my hand. I'm a master of calculus. You go find a double area integral in that calculus textbook. You try. You mean we're doing things in engineering which would be a stretch and a challenge for even, yeah, for your calculus. Yeah, absolutely true. It's a double area. Go and look in your solids books. Go and look in your dynamics. Go look in other books where you say, wow, that class was a lot of mathematics. And compare to what this class has been. This class has been mathematics on steroids. Excessive mathematics. That's what makes heat transfer hard. The fluid mechanics background required and the mathematical background required. So this is very challenging. I think you're starting to recognize, what is that, cosine theta I? Oh, that's the angle from the normal coming off that surface. And then theta J, oh, that's the angle from the normal going off of that surface. And R is the distance for each of those points, connecting lines. We'll get to this integral. Well, we're also going to have 2 rules beyond the equation for the view factor and a physical interpretation. We're going to have the summation rule, meaning that if you sum the view factors for any surface I, you sum over all surfaces J, it equals 1. The photons have to go somewhere in an enclosure. They're going to go somewhere. So for each surface I, the sum of its view factors summed over all surfaces j has to equal 100%. The other one is reciprocity. So the area I, view factor I to j, is equal to area j, view factor j to I. That looks pretty abstract mathematically, but it says this basically. If a surface I is sitting here and its photons are leaving it, and they're actually able to impinge and hit on surface j, guess what the photons from surface j can do? They could travel in the same straight line backwards and hit on surface I. So there's a reciprocity rule. Then we're going to be able to, this is the most important section of the whole chapter. Once you've mastered that, then we're ready to go and solve for black body radiation exchange in surfaces. We'll talk about some resistance. Just like we had L over Ka, conductive resistance, right? We can have a resistance for radiative exchange. What drives the radiative exchange is not the temperature, but it's sigma T to the fourth for each surface. It's the black body emissive power of that surface. So it's the watts per meter squared for each surface. And if it's high temperature, well then EB is high, and it's going to drive the radiant exchange in the network toward the cooler walls or cooler surfaces. So you're going to have a network of nodes. Connection between the nodes will have resistances, and the geometrical resistance is 1 over AI Fi to J. Hey, you're looking for cookbook? You can now turn it off. You can sleep. Right? The rest of the lecture is just going to be trying to explain these concepts. Here's the concepts, you got them down. Right? Just go for the equation sheet during the exam, you'll probably do pretty good. Did you bring your pillow? Bring it out. Sleep now. All right, we're not going to be able to get into grade diffuse surfaces. We will next time, but this time we're just going to be in this section 13.1 and 13.2. So we start the discussion talking about black surfaces. When you see a black surface, two things come to mind. Its emissivity is 1 and it's diffuse. Well, if its emissivity is 1 and its absorptivity is also 1, it's a perfect emitter and a perfect absorber. Any photons that hit it, they're going to be absorbed. And it emits the maximum fraction. The fraction of emission for the emissivity is 1, so it's the maximum of any surface at that temperature. All right, so let's talk about the emission that goes from surface 1 to surface 2. What type of notation do I want? Well, I'm going to think about little amounts, dQs, that leave 1, and I'll use this arrow notation, and that go to 2. And because both surfaces are black, I know the distribution of those that are leaving 1 is cosine distributed, and I know that they're going to be gobbled. If they impinge, they're going to be absorbed into surface 2. Well, if I wanted to calculate all of it that left 1 and impinged on surface 2, I would just do an integration, sum them all up. Well, we've done this before because the little dq is the I sub E leaving 1. What is the cap I for? Intensity. Subscript E, emissive intensity. Subscript 1, leaving surface 1. So the emissive intensity from surface 1, because it's diffuse, that's a constant, not a function of direction. All right. Multiply by dA1 normal. That's the little chunk area of 1, but it's the projected normal back in that direction of the photons that are leaving. All right. And we'll improve that in a minute. And then d omega. What's d omega? This is the solid angle from 1 to 2, the little solid angle. So I have a little chunk. So we're going to integrate over all the solid angles and integrate over all the area 1s. Okay, well, let's expand out. What is this? This I, E sub 1 can come outside the interval because it's a constant, isn't it, for a diffuse emitter? And then we have dA1. That's going to be the cosine of theta 1 times dA1. Think a little sketch up here. Here's my surface. This is the back side of the surface, so I'm only interested in the front side of surface 1. It has a little unit normal vector right there. We come over here, here's another surface. There's the back side of that surface. So this is the front side of surface 2. And it has a little normal vector right there. What we do is we draw a straight line from that point on 1 to that point on 2. The length of that line is r. We have this angle is theta 1, and that angle is theta 2. I know it's in 3D. It's hard for me to sketch it in 3D. The equations work and are written for 3D, but I've sketched it in 2D. Yes, sir.
Well, in the previous slide, you had theta j and theta I.
Yeah, I'm going to switch between I1 and 2 and I and j.
So it's based off the angle between the two surfaces, not from normal to the surface.
For each of them, they have a unit normal. And then for that particular direction that the photons have to leave 1 to hit 2, that location on 2, is going to be theta 1 defined, as well as theta 2 is defined. Yeah. All right. I have some questions that pertain to that in a minute. Let me get to there. So this gives me dA1 normal, and then the omega, the solid angle, that's going to be the cosine of theta 2, dA2, divided by r squared. And now we're just going to integrate over, because we transformed that solid angle into an area, integrate over area 1 and area 2. Double area integral. The emissive power of 1 and the intensity of emission of surface 1. What is the relationship that we have? Let me do this. Let me write it like this. If I take this and multiply by A1, that's the total, let me look at the units on this. Watts per meter squared times meter squared, that gives me the total power out. All right. I want to relate that to the intensity of the emission, but the intensity of the emission was, what units were they? Watts per meter squared, and I'm going to put normal times steradian, true? So to get this relationship, I multiply by the area of 1 and pi. Or maybe you remember it as E1 is equal to pi I e sub 1. How is the emissive flux related to the emissive intensity? Well, you multiply I by pi, steradians, and that's, you get E. This is what is Q1 leaving 1 and going to 2. Over here, what is Q that leaves 1 and goes to anywhere? Anywhere in the enclosure. Isn't that going to be E sub B1 times A1, which is, now I can use it as pi E sub, or intensity emission of surface 1 A1? Yeah, that's true. So if I'm interested now in getting the fraction of the energy that leaves surface 1 and goes to 2. So it's the fraction. So what I do is I'll say that fraction from 1 going to 2 is equal to Q leaving 1 and going to 2 divided by Q1 going anywhere. I just take and substitute. That's I e sub I. The double area integral, cosine theta 1, the cosine theta 2, dA1, dA2 divided by r squared. Divide by the pi e sub I1, A1. What cancels? The intensities cancel, and we're left with this equation. The view factor from 1 to 2 is equal to the double area integral of the cosine theta I, or 1. I keep switching back and forth. I and j are general or generic, and then sometimes use 1 and 2. Cosine theta 2, dA1, dA2 divided by, put the pi underneath the integral, r squared. 1 over A1. There it is. We've derived it. Believe me, first time you see the derivation, you're probably bewildered and overwhelmed. Hopefully not too much right now. But this is what I will say is a mathematical description of the view factor. All right? It's a double area integral. This is the physical. Don't lose sight of the physical. So if I was doing a numeric simulation, I was randomly tracking photons leaving a surface 1, I would say, okay, I'm going to send out 1,000 or 100,000 or 1,000,000 photons, right? And then I'm going to see where they go, do a little numerical checking where they go. And then I'm going to tally up the ratio, and that's my view factor. It's a fraction. If I do the emission of the photons numerically from a surface correctly, I'll be able to get a pretty good view of the estimate of that view factor. All right. So that view factor, in general, Fi to j. The book does not use Fi to j or any other notation like that. It's just Fi without a space j. So sometimes you'll get a little confused. Let's say the view factor from surface 3 to 4. Somebody may look at that and say, oh, it's the view factor 34. No, it's from the surface 3 to 4. Well, what happens if I start getting numbering of surfaces that are like 11 and 15, you know? The view factor 11 to 15. Well, it gets very, very complicated then, okay? And probably you're going to put a comma in there or something to help distinguish it. But for low surface counts, it's just ij, without a comma, without a little dash, without a little arrow. So it's the fraction of radiant energy that leaves diffusely from surface I. That means it's going out in that particular direction. It's a diffuse emitter and is intercepted by, or it lands on, surface J. All right, this double area integral is hard to show in 3D. I'll try to show a little bit of it in 2D. So let's take a surface here. The back side of the surface is just shown there. This is the front side of surface 1. All right. And then we'll have another surface. Let's draw it over here. And the back side. And then this is the front side of surface 2. You can see that the photons can leave this surface, go in that direction, that direction, that direction, that direction, and some of them will strike surface 2. All right. I would like to discretize surface 1 into little chunks. They're not going to be too little for illustration purposes. What did I bust it into? 1, 2, 3, 4, 5 little, sections of it. So I'm going to do the integration over 5 little subsections. Likewise, I can come over to surface 2. 1, 2, 3, 4, 5, 6, 7, 8 sections. Okay, for this, right here I would put out a unit normal vector and another unit normal vector. And each one of these sections has a unit normal vector. Because they're a curved surface 1, nothing restricts this to be a planar surface. Those unit normal vectors are little, they vary. Likewise over here, unit normal vector, unit normal vector, unit normal vector, unit normal vector, like that. Okay. Now what I want to do is I want to do a tally, a summation. So I think of going from this point to that point, that one to that one, 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 that one to that one. And for one part of surface I, I'm integrating, summing up over surface J, or it's the second surface. And for each one of these, I would have a different angle, theta 1, and a different angle, theta 2. And then I move to another one, do the same thing again. It's like ray tracing, etc. And then even all the way down to the end. Go from here to there to there. How many people do this mathematically? Oh, we are so lucky that other people have analyzed this to death and that have written textbooks and tabulated all the results and put them in those textbooks for us, or even computer codes. You're not the first to have to calculate a view factor. Aren't you happy? Yeah. So we can benefit from the work of others. Let's answer some questions. Is this the correct equation? Now it's written f I to j. Does it look good? 1 over area I, the double area integral. Each of these terms we understand. What is that r? That's that distance. Okay. All right. Also, we recall this is a mathematical description, a physical description. Think about how many photons or the rate at which photons are coming off of surface I and going and impinging on surface j, and normalize that to the radiant power leaving I and going anywhere in the enclosure, hitting all surfaces. Let's answer some questions. Can the view factor Fij equal 0? Can it be equal to 0? So everybody in? Let's go ahead and stop it then. Everybody in? So let's do this. Could I have an enclosure that looks like, I'm going to draw them in 2D. But think of the enclosures in 3D, but 2D. One surface like this, one surface like this, and the other surface like this. So that this is surface 1 here, surface 2 there, surface 3 there. Sure, no problem. Okay. Can I draw an enclosure that may have a surface like this? I'll have a surface 1 here, and I'll have a surface 2 here, 3 here, 4 here, 5 there. And basically, this is all right in here is surface 1. This is all surface 2. This is all surface 3. This is all surface 4. And that's all surface 5. You see what I'm trying to do? All right. Could the photons leave surface 1 and hit in a straight line surface 3? Let's answer this question again. Can the view factor Fi to j equal 0? All right, so we're going to go ahead and stop. It will show the results. And the view factor can indeed be 0. When will it be 0? When the photons of one leaving it can't go in a straight line and hit the other one. They're blocked. They're in the shadow of something else in an enclosure. Luckily, we don't run into that too often, just often enough that you know that, yeah, the view factor can be 0. Let's see how we did the first time answering that question. Actually, 8 people said incorrectly, and then 6 people. So all I was able to do was convince 2 people. Okay, let's move on. How about this one? Can the view factor be negative? Can it be negative? All right, I'm going to go ahead and stop. And there's 2 ways. Anytime you're confronted with a question like this or this, think about it either mathematically or physically. And physically is probably the better way of looking at it. And what would it mean if I sent out a million photons and then I tracked them and so many hit this surface? Well, I'd do the ratio and that would be an estimate of the view factor. How could I get a negative view factor? I have a positive number of photons being sent out. I have a negative number of photons that went from 1 to 2. What? The lowest number that can go is 0, and that's when it's in the shadow. It's blocked. They can't hit it. So it doesn't make sense to have a negative view factor. There's no negative view factors. Isn't that nice to know? Let's go ahead and grade this one. So, can the view factor be negative? No, cannot. Okay, 8 people. Well, let's see. Should I go with this one? Okay, the integrand in the view factor equation is given by this. cosine theta I cosine theta j divided by pi r squared. You can see this right here. That's the integrand right there. Can the integrand be negative at any location? Yes or no? All right, we're stopping. Stop. And now let's do this. Let's say that somehow I was doing the integration from surface 1 to surface 2, and at this location, the little dA on surface 1, and at this location, the little dA at surface 2, the integrand just happened to become negative, right? What I would do is I would just shrink area 1 to be just right around dA1, then shrink area 2 right to be around dA2, and then calculate it for those itty-bitty little surface areas, what would be the view factor from 1 to 2 for a small 1 and a small 2. It can never be negative. So the integrand has to always be positive. So, can the integrand be negative? No. It's always positive. It's hard to see mathematically. Somebody says, well, show it to me mathematically. Okay, what is the range of theta I? Could it be less than 0? Does it make sense to have a theta I less than 0? No, theta starts at 0, right? And it goes down. Remember, here's my unit normal. I'm doing theta in that direction. Well, what happens, Professor, if you're over here? Well, phi just went around and took us around, but this is still a positive theta. Okay, now, so what is if the minimum value of theta is 0, what is the maximum value of theta? Can theta go to pi over 2, which is 90 degrees, or can it continue to go to pi, which is 180 degrees? What is the upper limit on theta? It's 90 degrees. It's pi over 2. Yeah. And so as soon as it's pi over 2, what is the cosine of either 0? Oh, that's 1. The cosine of pi over 2? 0. The smallest, the cosine of any of those theta angles can be is 0. So maybe some of you were thinking, oh, what happens if I put in, a theta greater than 90 degrees? Well, yeah, the cosine would then be negative, but that doesn't make any sense physically. All right, let's press forward. Now we bring in to our rule, the summation rule. There's a couple of ways of doing the summation rule. Think of enclosure. Surface 1 here, surface 2 there, surface 3 there, surface 4 there, surface 5 there, right? And we say, what is, if I leave 1 and go anywhere, isn't that the sum of leaving 1 and maybe hitting 1? You're saying, that's crazy. How can it leave 1 and hit 1? Do this to 1. What did we just do to surface 1? We either made it convex or concave. I just changed the shape of surface 1. It's not a flat line anymore. Is surface 1 convex or concave? Concave. You know that the photons on this side of surface 1 could go out, hit surface 2, could go out, hit surface 3, but some of them could go over and hit surface 1. So you have to take into account that you may see yourself. The surface can see itself. So plus the amount that leaves 1 and hits 2, plus the rate or the amount that leaves 1 and hits 3, plus the amount that leaves 1 and hits 4, all the way up. Let's stop it at, I know I stopped it at 5, so let's stop it at 5. Q, 1 to 5. Does that equation make sense? If you go anywhere, you're going to go to one of the things that make up the enclosure. Well, if I take this equation and I divide it by Q1 to anywhere, 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 Q1 to anywhere. Did I do proper mathematics? Did I, divided every term in both sides of the equation by the same amount? Sure. And then what is this? 1. That's just 1. What is this? The view factor from 1 to 1. What's that term? The view factor from 1 to 2. What's this term? View factor from 1 to 3. What's that term? The view factor from 1 to 4. And the view factor from 1 to 5. Again, I'm assuming all of these are diffuse emitters. So now you can see the summation rule. So the sum of all the view factors from this surface 1 to any and all surface j's has to equal to 100%. That's the summation rule. We generalize it by saying for any surface I, the sum over all surfaces j, the view factors, has to be equal to 100%. There's also one other rule. It's called the reciprocity rule. Well, when I encounter a word like this, maybe I'm not so certain. What does reciprocity mean? Well, I would go to the online dictionary, encyclopedia, and look it up. But how about you from memory? What does reciprocity mean to you? Who's a volunteer? You volunteering? What you learned in kindergarten, when you punched somebody, they punched you back? Is that what you said? Pretty much, huh? You punch me, I punch you, huh? Tit for tat, either on a aggressive, warlike, or you give me a present at Christmas time, I give you a present at Christmas time. Maybe we make it more, happy, make reciprocity happier. But anyway, reciprocity is this notion that you have reciprocal behavior or action or influence. And so in this, what it is if I have a surface here, surface I, and I have another surface J, the photons that leave I, if some of them can hit J, guess what the photons from J can do? They can leave J, and some of them will hit surface I. They'll just go back and forth. The best way to see reciprocity is write the mathematical equation for it. So I know the last time when we showed summation rule, we started with this physical, thinking about flow of electrons, and not photons, not electrons, off into the enclosure. But here, just look at the mathematical. So the view factor from, you want to do it 1 to 2? It's a little easier than I to j, is equal to 1 over the area 1, the double area integral of the cosine theta 1 cosine theta 2 divided by pi r squared dA1 dA2, and you're going to integrate over area 1 and area 2. Does it really matter the area order? I mean, can I integrate it first over area 2 and then 1? Yeah, we remember that in calculus. A lot of these integrals, you can go with this one first and that one second. If I write it for the view factor 2 back to 1, it's 1 over area 2, area integral 2, area integral 1, cosine theta 2 cosine theta 1 divided by pi r squared dA2 dA1. What do you think I do here to develop the reciprocity rule? Take this term, put it up there, so we have A1 times F1 to 2. Take this term, put it up there, so we have A2 F2 to 1. And then we take a look at what's left on the right-hand side of both of these equations. They are the SAME. They're the same. So the reciprocity rule can be written as area 1, view factor 1 to 2 is equal to area 2, view factor 2 to 1. Does this mean the view factor 1 to 2 is equal to view factor 2 to 1? No. That's not true. But this is true. Okay, it's an area times a fraction is equal. So A1 F1 to 2 is equal to A2 F2 to 1. Say it 10 times, it'll roll off your tongue easier next time. All right. Are there any enclosures with two surfaces? Sure, a lot. They're simple. They're easy to analyze, so often in this type of class we beat you up with them. Okay, so let's think about two concentric spheres. So here's the center of the first sphere, and here's the center in the same location of the center sphere. And so we're interested in the outside of the first sphere and the inside of the second sphere. That makes the enclosure. between the two spheres. Okay. Calculate the view factors for the enclosures. So you're going to be asked to calculate from 1 to 1, what is that view factor? Also 1 to 2, what's that view factor? Then the view factor 2 to 1 and the view factor 2 to 2. For a two-surface enclosure, there's really 4 view factors you can calculate. All right? What are the methods we're going to use to calculate these view factors? First of all, we're going to use observation. We're just going to look at it, and we're going to think of the physical interpretation of the view factor, thinking of photons leaving a surface, and we're going to think about, oh, can the photons leave that surface and hit this surface? Yes or no? I mean, pretty obvious, but sometimes that's what it is. All right, then the other that we're going to use a lot of is a summation or reciprocity. Summation rule and the reciprocity rule. Okay, so I have 4 view factors here. What I'm going to do is I'm going to pause, I'm going to walk around, and I want to see how many of these 4 you can calculate. No quiz today. So let me pick it up here. A lot of people were able to say 1 to 1 is a 0. How do they do that? By observation, summation rule, or reciprocity? Which one? Observation. Oh, is surface 1, it's like a solid sphere here. And the radiation's happening in the annulus region between the two. Okay, so can the photons leave 1 and hit 1? No. Is surface 1 concave or convex? Convex. Convex. That's, hey, I'm trying to help you with your math. All right. So from summation, now we move to summation. The sum of the view factors from 1 going to anywhere is equal to 100%. So F1 to 1 plus F1 to 2, since there's only 2 surfaces in the enclosure, have to equal 100%. We just concluded that was 0. Hence, from summation, you get the view factor 1 to 2 is 1. So this one was observation, then summation. Then think about coming down here and doing reciprocity. What do you mean by reciprocity? Well, I have that the area 1 view factor for 1 to 2 is equal to area 2 view factor 2 to 1. In this equation, the only thing I don't know is view factor 2 to 1. So the view factor 2 to 1 is equal to area 1 divided by area 2 times the view factor 1 to 2. But that view factor 1 to 2 is 1. And so this is just area 1 divided by area 2. This is equal to 1. All right. And then how do I get the very last one? Summation. So 100% is equal to the view factor 2 to 1 plus the view factor 2 to 2. So the view factor 2 to 2 is 1 minus the view factor 2 to 1. 1 minus A1 divided by A2. Done. If I would give you the diameters, you'd be able to compute those numerically. Ready to press on? All right. We have 2 inclined parallel infinite plates of equal width. So they're infinitely long in the direction of the paper, the slide here. And their width is W and W. And they have a common edge, this dot right there, and they're separated by angle alpha. That's the angle between the two. And alpha can be small or large. Okay, so 1 is the surface of the top plate looking down. 2 is the surface of the bottom plate looking up. And there's this view factor relationship that the view factor from 1 to 2 is equal to 1 minus the sine of alpha over 2. How did they derive that? Well, it's going to use 3 things. You're going to use observation. Don't turn your brain off. You're also going to use summation. And you're going to use reciprocity. So let's do the derivation fairly quickly. what we introduce is a enclosure. I have to get an enclosure, so I introduce a third surface right here, surface 3. Okay? All right. Can you tell me the length of 3? The length of 1 is W. The length of 2 is also W. We're talking lengths, right? If you multiply by the depth of it, you would have the area. But in 2D, length is equivalent to the area. It's infinitely long in that third dimension. Okay, so what is the length of surface 3? Well, you'd come over here and you'd probably do this. I'm going to cut this into 2. And do I have one of my most favorite triangles? Do I have two of them, right? Of my most famous, favorite triangles. What are those triangles? They're right triangles. They're your old friend. And so the length of this side is the hypotenuse, W, of that right triangle, times the sine of alpha over 2, because that's, if I cut it in half, then the angle is alpha over 2. So the total length of 3 is 2W sine of alpha over 2. Very good. What's the next step? Well, I'm interested in some of the view factors. Let's think about the view factor from the perspective of surface 3. 3 to 1, view factor 3 to 2, and the view factor 3 to 3. Who would like to volunteer to give me one of them? Somebody in the front row. There you go.
3 to 1 is going to be 0.5.
Okay, 3 to 1, you took the hard one, is 0.5. Okay, staying with the front row, somebody give me the easy of these 3 view factors. There's only 2 left now. 3 to 3 is 0. How did you get that? Use your brain. It's a flat surface, neither convex, concave. Now, what do you do to get that both of these are a half? You had to jump through some logic to get to that. But other people may take more steps to get the same path, to get to the same end conclusion. Basically, it's symmetrical about that cut. And so 3 sees 1 with the same ease at which 3 sees 2. And so the view factor from 3 to 1 is equal to view factor 3 to 2. They're equal, and they have to sum to 1 because it's an enclosure, hence it's half and half. Very good. Now, once I know that one, what I can do is I can say from reciprocity, what is the view factor from 1 to 3? Isn't that A1, F1 to 3 equal to A3, F3 back to 1? Yeah. And so the view factor 1 to 3 is the area 3 divided by area 1 view factor 3 back to 1. So it's 1/2, that's the view factor from 3 back to 2, or 3 back to, did I say 3 back to 2 or 3 back to 1? 3 to 1. And then what is the area 3? 2W sine of alpha over 2. And what is the area 1? W. The 2 W's cancel. The 2's cancel. And so the view factor from 1 to 3 is equal to sine of alpha over 2. I pause. Does that look okay? Or not? So, guess what we do now? We already used reciprocity. We've used observation. Use summation. So if you have the view factor from 1 to 1 plus the view factor 1 to 2 plus the view factor 1 to 3, is that equal to 100%? One of these is 0. So the view factor 1 to 2, that's what we set out to try and calculate, is equal to 1 minus the view factor 1 to 3. It's 1 minus the sine of alpha divided by 2. QED. Make sense? You ready to press on? All right, let's press on. We have a radiative exchange between two black surfaces that make up an enclosure. Let me kind of go over some of these. You could have two infinitely large parallel plates. This is the back side. We're only interested in radiative exchange on that side, which can see and go to this side too, and at the back side, like there, okay? That would be an example of the radiative exchange between two surface enclosure. All right. You could have a sphere inside of a sphere. You could have a pipe infinitely long inside an infinitely long pipe. You could have a hemisphere covering a disk. There's a lot of two-surface enclosures out there. Well, let's just think about a simple one. Do you want to do the sphere inside of a sphere? Whatever. We just did that one, right? So this is surface 1. That's surface 2. I'm interested in calculating Q, the net transfer from 1 to 2, but also there's going to be some flow back and forth. So you have to say, well, this is what leaves 1 and goes to 2, and if it hits it, because 2 is black, it's absorbed. And then I have to subtract off the amount that's leaving 2, going back to 1 and hitting, and then is absorbed. That would be the net exchange. Okay? So what is the Q that leaves 1 and gets to 2 and is absorbed on 2? Well, it'll be the EB1 times the A1. That'll be the net power, watts of radiant energy leaving 1. I multiply by the fraction that gets to 2. We subtract off EB2 times A2, F2 back to 1. And then we say to ourselves, from reciprocity, are these the same? Is A1, F1 to 2 equal to A2, F2 to 1? Yeah, they're the same. So what you can do is combine it, and you can say either one. Put A1, F1 to 2 times EB1 minus EB2 is equal to the Q1, and this is where, you could write net, and you put this double arrow like that, or you could just put Q1, 2. That's how I think the book does, just like the view factor 1, 2, or IJ. No comma in between it, no little arrows. Okay, so this is our flow. And this is what drives the flow. This is our difference in the potential. And then way back we had our little review of this little thing right here. We had the voltage here and the voltage there, and we had the flow of the current through that. And this is a resistor, and there was somebody's law. I forgot the name of that person's law with resistors. Ohm's law. Ohm's law. That's exactly right. And Ohm's law had that the flow of current is equal to the difference in what drives the flow of electric current, which is the EMF, the electromotive force measured in volts, divided by the resistance, the electrical resistance. And we did the same thing when it came to heat transfer through a slab, didn't we? We had Q is equal to T1 minus T2 divided by the resistance L over Ka for a slab. All that's good little review. All right. Here what we do is we say, oh, I have a flow from 1 to 2. It's what drives it, a difference in the black body emissive powers or fluxes, because it's watts per unit area. You divide by 1 over A1 F1 to 2. This is resistance, geometrical resistance, geometrical resistance for radiative exchange between two surfaces. It's equal to 1 over A1 F1 to 2. Name calling, and it helps us in bookkeeping. So what we can do is we can have a node and a node. What drives the flow EB1, EB2. What resists it is 1 over AF, a geometrical resistance. What comes into our network? Our Q at that node, 1. It would then flow through. And here what we're going to do is I'm going to try to be consistent. I'll put Q2 into node 2, but you could tell Q2 has to be negative of Q1 for energy balance for the whole network. All right. Consider 2 large parallel black plates with the top plate is at a surface temperature of 1200 Kelvin. The bottom plate is at a surface temperature of 400 Kelvin. And so they face each other. And we want to calculate the net radiation exchange per unit area between the 2 plates. So the photons are being sent from 1 down to 2, but 2 is sending photons back up. All right? So we would introduce a little network. We would have EB1 and EB2. What is EB1? Sigma T1 to the 4th. What is sigma? 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th. What is our temperature for surface 1? 1200 Kelvin all to the 4th power. You get that. You'd be so many watts per meter squared. Likewise, this is sigma T2 to the 4th. Well, that's the potential which drives it. What's our resistance? It's 1 over area 1, F1 to 2. Okay. And then this is our Q1. So if we wrote our equation for an energy balance around this node, what you would say is Q1 into the node is equal to what is flowing through this resistor. And that what flows through the resistor is EB1 minus EB2 divided by 1 over A1 F1 to 2. You're saying you're making this so complicated, Professor. I know. It's a big stick for a small problem, but we're going to use the same approach when we have a more complicated network. So we have Q1 divided by A1 is equal to, then you're going to have the view factor 1 to 2, EB1 minus EB2. This is what we wanted to calculate. It's our net radiation exchange per surface area between the plates. And so the view factor is 1, and we had the Stefan-Boltzmann constant, 5.67 10 to the minus 8. And then we had the T1 to the 4th minus T2 to the 4th. And in the interest of time, I'm just going to say that that turns out to be 116 kilowatts per meter squared. Does that problem look good? We're going to vary. Now we're going to change this problem just a little bit and resolve it. We're going to have the same top plate temperature, the same bottom plate temperature, but we're going to introduce what we call a radiation shield. All right. So the radiation shield. So what we introduce is a thin opaque sheet which is introduced between the top and the bottom plates. So the top, still 1200 Kelvin. The bottom, still 400 Kelvin. And a plate. Didn't say the temperature of the plate anywhere in the problem. It's thin, it's opaque. What does the opaque mean? Photons can't go through it. The photons that are coming from here are going to get absorbed on that side of the plate. The photons from here are going to be absorbed on that side, of the bottom side of the plate, or the shield. And the bottom side of the shield sending photons down, and the top side of the shield sending photons up. So let me ask this. There's another key word, thin. All right. What is the difference, do you think, about the temperature on the top side of the plate and the temperature on the bottom side of a thin plate? Same. You see how good you are? This is good. Because if you don't make that observation, we have a long problem. You know what? If the plate has some thickness and the temperature on the top is different than the temperature on the bottom, then I need to know the thickness and the thermal conductivity, and it's going to be conduction through that plate. That's going to add resistance to the heat transfer from the top to the bottom. So I'll have radiative then I'll have conductive, then I'll have radiative again, and that is a multi-mode heat transfer problem. Guess what? Multi-mode heat transfer problems we're going to save until another day. All right, where we have conduction and radiation occurring. So, but let's jump back to this problem. So, what we do is if they are the same, these are the same, what about the EB on the top and the EB of that on the bottom of that side, you know, that foil, that shield? They're the same. They're the same. So what I'm going to do is I'm going to just have a node for the EB in the middle. Let's call it surface 3. We'll have a node for EB1 and we'll have a node for EB2. I know I could have reordered them, but let's leave EB2 on the bottom. We're going to have a resistance and a resistance. This is a 1 over AF. This is a 1 over AF, geometrical resistance. So we do the same thing. We want to get this Q going in. We want to get Q divided by A. Now, because we just put an extra resistor in there, they have the same magnitude. Can you guess what it did to the Q over A? Did it double it? Did it leave it alone? Or did it cut it in half? It was 116 kilowatts per meter squared. Is it now 232 kilowatts per meter squared? Or is it half of that? 58 kilowatts per meter squared. Which one do you think it is? The 58. I hear the 58. Anybody else? Yeah, it's added resistance. Just by putting in something. And it's a great absorber. If you want to even make this a better shield, put in a piece of foil that has a low emissivity. I know we're getting ahead of ourselves, but a low emissivity is a great radiant foil. We'll do that next time. But even a poor radiant shield, a black radiant shield, will cut that radiation heat transfer, and it'll cut it in half. Just go ahead and do the math on that, okay? All right, let's press forward in the interest of time. Okay, you can solve 3 surface enclosure problems as well as 2 surface enclosure problems. Let's pick one out. Don't make it too complicated. Here's surface 1. There's the back side of it. Then here's surface 2, the back side of it, and surface 3, and that makes up our enclosure. So this is surface 1, surface 2, and surface 3. All right. How would I solve for the exchange between 3 black surfaces that make up an enclosure? I would put EB1, I would put EB2, and I'd put EB3. If I knew the temperatures of some or all of those surfaces, I could know the EBs of all of them because they are just sigma T2 to the 4th, etc. All right, what do I have between them? Some geometrical radiative resistance, 1 over area 1 view factor 1 to 2, 1 over area 1 view factor 1 to 3, 1 over area 2 view factor 2 to 3. Somebody says, why don't you write that as 1 over area 3 view factor 3 to 2? It's the same, reciprocity. Okay. Then I like to put in that the Q1 is what's being supplied to surface 1. Q3 is what's being supplied to surface 3. And Q2 is what's being supplied to surface 2. From an energy balance, Q1 in plus Q2 in plus Q3 in must equal to 0. That's the total energy balance for entire system. So some of them, if 1 or 2 is positive, the other is going to be negative. To solve this problem, is I come in and I do an energy balance for each node. So we have an energy balance for node 1. Let's go ahead and write that. What's that look like? It would be Q1 in plus, and then this is the way I write it, is these are outs flowing away. Okay, you could write it the other way. It doesn't matter. Okay, do you want to write it the other way? Fine. We could write them going in then. Everything's going into the node. That's fine. So Q1 in plus what flows through this one resistor is going to be EB2 minus EB1 divided by 1 over A1 F1 to 2. And then what flows through that the bottom resistor is EB3 minus EB1 divided by 1 over A1 F1 to 3. And the sum of those has to equal 0. You can write the energy balance for node number 2. Come up here. There you go. And you can write the energy balance for node number 3. You know, this sure does look like a lot like that finite difference approach to conduction heat transfer that we covered. Sure does. Very much so. So we have energy balance for each nodes. How about, should I write one for the third node? Let's write it for the third node. So we have Q3 coming in. Then I'm going to write it like this and like that. And so it's going to be plus EB1 minus EB3 divided by 1 over A1 F1 to 3 plus EB2 minus EB3 divided by 1 over A2 F2 to 3. That's equal to 0. You can set up the equations. This problem has different unknowns than that problem, and then you just solve. Okay? All right. I don't think I have time for this problem. I guess I'm going to have to stop here. Thank you very much for your attention. We'll see you next week.